Okay, so section 5.1 is about series solutions about ordinary points. And what we're actually going to do is we're going to break up that section into two parts. The first part is going to be about series basics. And what we're going to do here is we're going to recap what an infinite power series is. We're going to talk about convergence of these things, how we do arithmetic and derivatives with them, and then this idea of combining series, which is going to be important later. So all of this is going to be stuff that you probably learned or talked about in another class, maybe calculus, but we're doing it again because that tends to be a very difficult thing when people learn it, and being able to confidently work with series is important for this section. So just to start off, let's talk about what a power series is. So oops. This is something we're going to be working with for the rest of class. And a power series is an infinite series that has this special form to it. And so it's some function of x, and it's an infinite sum. That's what a series is. And then it's going to look like this: some c sub n times x minus a to the nth power. And so what that looks like when you kind of imagine plugging in from n equals 0 to some number, we would go on forever to infinity. But when you plug in n equals 0, you'll get c0 times x minus a to the 0th power, so that's 1. So you just get c0. And then you'll get c1 times x minus a, because you'll get c1 times x minus a to the first power, like that. And it's an infinite sum, so we add these things together. And then c2 x minus a squared, so on and so forth. That one coming from, I plug in n equals 2, c2 x minus a squared. And that's how it's built. So kind of the important part of how this is written is that right here is the coefficient for each term. Right here is something that tells me I'm kind of considering values x near a to some power. And I am taking an infinite sum. What's important here is that this series is centered around a for some number a. So I could do like x minus 2. That would be fine. And you might remember that when you learn these series, it would have been because a power series is a function of x that kind of can approximate some functions. So a power series So just from the way it's written right here, you should be comfortable with the idea that a power series is a function of x. It's something that takes in x and spits out this infinite sum. The reason they're valuable is because they approximate other functions. Other functions. Well, let's say can be used to approximate other functions. Because the way I've written one down right up above, that doesn't necessarily mean it's approximating anything. And the specific way you might have talked about this was in terms of using Taylor series. So Taylor series still exist. Infinite representations of certain functions. And so you would have learned that you can use them to write things like e to the x or cosine x as infinite sums of powers of x. So for example, e to the x would have been something like 1 plus x over 1 factorial plus x squared over 2 factorial, so on and so forth. And then you could like approximate by saying, okay, e to the x, if I wanted to calculate it, could be sort of close to 1 plus x over 1 factorial plus x squared over 2 factorial, so on and so forth. But I stop at, let's say, 100. So that's a Taylor series approximation. And the first thing is an infinite power series that would have been represented with n equals 0 to infinity of x to the power n over n factorial is what that looks like. So here's like our n equals 2, x squared over 2 factorial, for example. So you might be wondering sort of like, why does this matter? And the reason we're going to talk about this is because since you know you can do this for a lot of functions, maybe if you're looking for the solution to a differential equation, it's one of these functions that can be represented by an infinite series. And so you can use that to help you find a representation of your solution. So writing this all down, since many functions have an infinite series representation, maybe we can use those representations to solve an ODE. And what this is going to look like for us is we're going to plug series into differential equations and see what happens. Remember, plug it in and see what happens is a really common approach we took to differential equations during exams 1 and exams 2. Exams 1 and 2, sorry. And so this is a continuation of that approach, but this one uses infinite series as the thing we plug in, and so it can just be a little bit intimidating because of that, because series tend to be a little less familiar than, you know what e to the mx is. It's harder to visualize what infinite sum Cn x minus a to the n is. So we're going to go really slowly through properties of power series that you're going to need in order to use this tool. But even though we're going to have that very long aside where we build that foundation, I want you to bear in mind that the reason we do it is just because we're going to plug series into ODEs. It's going to turn a differential equation into like basically an algebra problem, and that's going to mean that we can solve the problem. So in the next video, we'll actually talk about some of those properties.